Have you ever really thought about what controls how fast your phone charges? Or, on a totally different scale, how we manage to pull energy from deep within the Earth? Well, believe it or not, it all comes down to a single, really powerful concept. And today, we're going to unravel exactly what that is. Okay, so to get our heads around this, I want you to imagine something. Imagine you're trying to navigate a maze, but it's a maze you can't even see. We're talking about these microscopic, completely twisted pathways inside, say, a tiny piece of rock or inside a battery electrode. That is the fundamental challenge we're tackling today. So, scientists have a name for this, of course. They call it tortuosity. It's basically just a number that tells you how twisted and convoluted all those internal pathways are. Simple enough, right? Well, not exactly. Here's the kicker. For decades, scientists were using this one single word to describe two completely different things. And that little bit of confusion, it's had some really big consequences. We're about to see just how big. All right, so here's the roadmap for today. We're going to trace the story of this idea, starting with a map of the invisible, then a big mistake called the shortest path fallacy. We'll use a cool analogy, Google Maps versus Waze, to understand it, see how it helps solve a real mystery in shale rock, and then explore what happens when the rules of physics change at the nano-scale. And finally, we'll see how this all leads from just taking pictures to making powerful predictions. Okay, first up, the shortest path fallacy. We're going to start with the most intuitive way to think about tortuosity. It's an idea that, well, it makes perfect sense on the surface. But as you're about to see, it's totally flawed when you try to use it to predict what happens in the real world. So this first, most obvious approach is called geometric tortuosity, and it's exactly what it sounds like. Just think of it like a super basic GPS. A computer algorithm literally just finds the one single shortest path from point A to point B through the maze. I mean, that sounds pretty logical, doesn't it? And this really gets us to the core of the problem. On one hand, you've got this simple geometric method, the intuitive way, but it gives you misleading results because it just ignores physics. On the other hand, you have what's called the tortuosity factor. This is the right way. It simulates the total flow, it's based on physics, and it gives you results you can actually use to make predictions. So why is this shortest path idea so wrong? Well, it has two major flaws. First, it completely ignores bottlenecks and constrictions. It's like a GPS that can't tell the difference between a 6-lane superhighway and a tiny dirt track. It just sees a line on a map. And second, it ignores all the other available paths. It makes this fatal assumption that every single particle is going to line up and take that one exact same route, which, that's just not how flow works in the real world at all. All right, let's make this even clearer. To really get the difference here, we're going to use a brilliant analogy that makes this whole thing click. Think of it as Google Maps versus Waze. This simple comparison is really the key to understanding the old, flawed way of thinking versus the new, much more accurate one. Okay, check this out. It really is the perfect comparison. Geometric tortuosity, the old way, is like Google Maps. Its logic? Just find the single shortest path. It only considers path length. But the tortuosity factor, the better way, is like Waze. Its logic is to simulate the total traffic flow. It's not just looking at length, it's looking at resistance and bottlenecks. One is just geometric pathfinding. The other is a full-on physics-based simulation. The result? One is a poor proxy for real flow, and the other is a robust, accurate predictor. So yeah, this Google Maps way of thinking, it finds that one single route, and it's totally blind to everything else. It doesn't see traffic jams, it doesn't see how narrow the road is, all it cares about is distance, which makes it a pretty terrible proxy for how things actually move through a material. Now, the Waze thinking is a total game changer. It's not just finding a path. It's simulating all possible routes at once. It's basically running a virtual physics experiment on the 3D map. By applying a sort of virtual pressure from one side to the other, it calculates how the entire network resists that flow, automatically taking into account every single twist, turn, and bottleneck without you having to find them one by one. Okay, so this Waze method sounds way better in theory, but does it actually work in the real world? Well, let's put it to the test. We're going to look at a case study involving shale rock, which, as you know, is super important for natural gas. All right, so here was the mystery with shale. Shale is formed from these flat, stacked clay minerals. Just picture a deck of cards. Now, scientists knew for a long time that gas flows really easily parallel to those layers, with the grain, but it really struggles to flow perpendicular to them, or against the grain. The challenge was, could they actually prove that this difference was because of the microscopic pathways just by looking at a 3D image? And when they ran the Waze simulation, boom, the answer was crystal clear. Just look at this. The tortuosity factor, that measure of flow resistance, was way, way higher when they tried to push the flow against the grain compared to with the grain. It wasn't even close. This right here, this was the missing link. It was the first time they had actual 3D, physics-based proof that directly connected the microscopic structure they could see in the image to the real-world properties that engineers desperately needed to understand. It proved the convoluted path was the reason for the massive resistance. But of course, science never stops, right? Just when they thought they'd solved it, solving this one problem actually revealed another, even deeper one. Because what happens when the maze gets really, really small, like nano-scale small? Well, that's when the rules themselves start to change. Okay, so in pores that are relatively big, gas molecules act kind of like a liquid. They're constantly colliding with each other. In this situation, our Waze model, the tortuosity factor, works perfectly. This is what's known as the continuum regime. But get this. In the super tiny nanoscale pores you find in shale, the rules of the game just completely flip. We enter what's called the Knudsen regime. Here, the pores are so incredibly narrow, the gas molecules are way more likely to collide with the pore walls than they are to ever bump into each other. Think about what that means. A gas molecule starts acting like a pinball, just bouncing off the pore walls over and over again. And every single one of those bounces adds a tiny bit of friction, a new source of resistance that our standard Waze model just wasn't built to account for. And because it misses all this extra pinball friction, the model actually ends up overestimating how easily gas can flow. It gets the answer wrong. All right, so let's just take a step back and recap this whole evolution, this journey from just looking at pictures to making real, accurate predictions about how things work. It's really been a 3-level journey. We started at step 1 with geometric tortuosity, that flawed shortest path idea. Then we moved to step 2, the tortuosity factor, our robust Waze model that works great for larger pores. And that's led us to step 3, the Knudsen Tortuosity Factor, the advanced pinball model that you need for the nanoscale. It's an amazing progression. And this is really the whole point. The ultimate power here is moving beyond just seeing a 3D structure. It's not about making pretty pictures. It's about turning those pictures into a virtual lab where you can accurately predict a material's real-world behavior. It's a total game changer. And that brings us right back to where we started. The complex, twisted pathways inside your smartphone battery, they're what determine how fast it can charge. This science is literally in the palm of your hand, which leaves us with a pretty cool question to think about. What other everyday technologies depend on navigating an invisible maze?